Chapter 6, Module 6. In this module, we shall mainly discuss two very important theorems. One is called Brouwer's fixed point theorem and the other one is called BorsaCoulomb theorem, both in dimension 2. In the introduction of algebraic topology, we have pointed out that fundamental group functor transforms a topological problem to a problem of algebra, thereby drawing conclusions about the solution to the original topological problem. In this module, we shall see how it really does. In what follows, the closed disk is denoted by D2. The boundary of the closed disk D2 is denoted by S1, and a function f is said to have a fixed point x if fx equal to x. Now we state Brouwer's fixed point theorem. It says that every continuous function f from D2 to D2 has a fixed point. So let us prove it. Suppose f is a continuous function from D2 to D2, and if possible, suppose that it has no fixed point, that is, fz is not equal to z for all z belonging to D2. Now consider the ray 1 minus t fz plus tz whenever t is greater than or equal to 0. Then this ray starts from fz and passes through z. This ray will meet the boundary S1 at some point. Let us call that point gz. Then we get a continuous function g from D2 to S1 given by z goes to gz, such that gz equal to z for all z belonging to S1. Consider the following diagram where I denotes the inclusion map. So I is a map from S1 to D2, g is a continuous function from D2 to S1. So this sequence of continuous functions induces another sequence of homomorphisms between the respective fundamental groups. So this new sequence is pi 1 S1 to pi 1 D2, we have the corresponding induced homomorphism I sharp, and from pi 1 D2 to pi 1 S1 we have the induced homomorphism G sharp. Now since D2 is a closed disk, it is contractible and therefore the fundamental group of D2 is isomorphic to 0, that means it is a trivial group, and on the other hand pi 1 S1 is the cyclic group of integers z. By functorial properties of fundamental groups, G sharp composed I sharp is equal to G composed I sharp, which is equal to the identity function on S1 sharp, but that is again by the other functorial property is identity on pi 1 S1, showing that identity map on Z is factoring through the trivial group 0, which is impossible. Hence, such a G cannot exist, and so there is some Z in D2 such that fz is equal to z. Now we define an antipodal point. Suppose I take a point x from Sn, then the diametrically opposite point minus x on Sn is called antipodal point of the given point x. Now, a map H from Sn to Sm is said to be an antipode preserving map if H of minus x is equal to minus of Hx for all x belonging to Sn. Now, we come to an example that suppose R phi is a map from S1 to S1 which stands for a rotation by an angle phi, that is R phi of cos theta sin theta is cos of theta plus phi sin theta of plus phi, then R phi is antipode preserving. Now, it can be seen easily that for the point z, which is cos theta sin theta, minus z is the point cos pi plus theta sin pi plus theta, and so R phi operated on cos pi plus theta sin pi plus theta is equal to cos of pi plus theta plus phi sin of pi plus theta plus phi, which is equal to minus cos theta plus phi minus of sin theta plus phi, and that is equal to minus of R phi cos theta sin theta. Now, the following are very useful observations about antipode preserving maps. First is that the composition of two antipode preserving maps is again antipode preserving. Secondly, if H from S1 to S1 is homotopic to a constant map C from S1 to S1 by the homotopy capital H, and R phi is a rotation, then R phi composed H is homotopic to a constant map C1 by the homotopy R phi composed capital H. In other words, H is null homotopic implies that R phi composed H is null homotopic. Now, we wish to prove what we call BorsaCoulomb theorem for dimension n equal to 2. But before proving this theorem, we need another theorem which states that there is no continuous antipode preserving null homotopic map from S1 to itself. Once again, in order to prove this, we need another concept, that is the concept of covering projection. So, we define what do we mean by covering projection and state a theorem which is the path lifting property of covering projection. We now start with the definition. Let P be a continuous surjection from a topological space x tilde to x. An open set U of x is said to be evenly covered by P if P inverse U is expressed as disjoint union of open sets V alpha of x tilde such that P restricted to each V alpha is a homeomorphism of each V alpha onto U. This collection V alpha is called the partition of P inverse U into slices, and each V alpha is called a sheet over U. If each x is taken from capital X, has an open neighborhood U in capital X such that P inverse U is evenly covered by P in x tilde, then P is called a covering map or covering projection, and x tilde is called the covering space of X. Such an open neighborhood U of X is referred to as an admissible open set. Now we state path lifting property of this covering map P from x tilde to x. Suppose P is a covering map from x tilde to x and alpha be a path beginning at some x0 belonging to capital X. Given any point x0 tilde in capital X tilde with P x0 tilde equal to x0, there exists a unique path alpha tilde in x tilde starting at x0 tilde such that P composed alpha tilde is alpha. Then this alpha tilde is called a lift of alpha. So that means whenever a path alpha in x is given such that the path begins at some point x0 in capital X, then there exists a unique alpha tilde from I to x tilde such that the diagram commutes and the initial point of alpha tilde coincides with the point x0 tilde which is mapped to x0 via the function p. We state a theorem now. If h is a function from S1 to itself such that it is continuous and antipode preserving, then h is not null homotopic. We start with proving it. Suppose B0 is a point taken from S1, that is the special point ordered pair 1 0, and suppose that the image of B0 under the map H is A0. If B0 and A0 are same point, then we proceed with the function H. If not, then choose a rotation R phi such that R phi composed H B0 is equal to B0. And in that case, we consider the map K equal to R phi composed H. In view of the previous observations, it follows that K from S1 to S1 is a continuous and antipode preserving map such that KB0 equal to B0. For proving that H is not null homotopic, it is enough to show that K is not null homotopic. Consider a map Q from S1 to S1 given by Q cos theta sin theta equal to cos 2 theta sin 2 theta. Then Q is a closed continuous surjection and hence a quotient map. The inverse image of any point W on S1 under the map Q consists of the antipodal points Z and minus Z of S1. That is, W equal to QZ equal to Q minus Z, and therefore Q of K minus Z equal to Q of minus KZ, and that is equal to Q of KZ. So, by the property of quotient maps, Q composed K induces a continuous map F from S1 to S1 such that F composed Q is equal to Q composed K as shown in the diagram. It is to be noted that B0 equal to Q B0 which is equal to Q K B0, and that is equal to f of q b0 equal to f b0. Also, k of minus b0 equal to minus b0. So, applying the fundamental group functor, we get the following commutative diagram. In the diagram, we have q sharp composed k sharp is equal to f sharp composed k sharp. We first check that such q is a covering projection. Now, for that, we start with 4 open sets of S1. First one is U1, second one is U2, third is U3, and the fourth one is U4. We can see that Q inverse U1 is the disjoint union of the points on S1 belonging to the first and the third quadrant of R2, each of which is homeomorphic to U1. And similar thing happens for U2, U3 and U4. We also observe that if alpha is any path from B0 to minus B0 in S1, then the loop beta is equal to Q composed alpha represents a non-trivial element of pi 1 S1 based at the point B0, because alpha is a lift of beta which starts at B0 but does not end at B0. Now, class beta, when plugged in, the expression of f sharp is equal to class of f composed beta by the definition of induced homomorphism, and that comes out to be equal to q composed k composed alpha class. Since k composed alpha is a path in S1 that starts from B0 and ends at minus B0, class q composed k composed alpha is non-trivial. Hence, f sharp is a non-trivial homomorphism from an infinite cyclic group Z to itself. So, it is injective. Similarly, q sharp is injective, so that f sharp composed q sharp is injective. Now, using the previous diagram, q sharp composed k sharp is equal to f sharp composed q sharp, and therefore, q sharp composed k sharp becomes an injective function. Hence, k sharp is injective and hence it is non-trivial. Since k sharp is injective, k cannot be null homotopic. We now state another theorem which says that there is no antipode preserving map G from S2 to S1. If possible, let there be a continuous antipode preserving function G from S2 to S1. Now, let us assume that S1 be the equator of S2. Then G restricted to S1 is a continuous antipode preserving map. G restricted to S1 is not null homotopic. It is known that the upper hemisphere E of S2 is homeomorphic to the 2 disk D2 and D2 is contractible. consider the continuous extension G restricted to E of G restricted to S1. Then we have the sequence of functions like this, that psi is a homeomorphism from D2 to E and G restricted to E is a continuous function from E to S1, and this gives rise to the non-trivial induced homomorphism G restricted to E sharp from pi 1 E to pi 1 S1. Now, since psi is a homeomorphism, pi 1 D2 coincides with pi 1 E and D2 is contractible, so pi 1 D2 is 0. But that is an impossible situation. Finally, we state BorsaCoulomb theorem. It says that if f is a function from S2 to R2 which is continuous, then there exists a point on S2 such that f of minus x is equal to f of x. If possible, suppose for all x belonging to S2, fx is different from f of minus x. Then we can define a function g from S2 to S1 by gx equal to fx minus f minus x whole thing divided by norm of fx minus f of minus x. Certainly, if f of minus x not equal to fx, then the denominator will never be 0, thereby giving a point gx on S1. Then g is a continuous function and we can check that g of minus x is equal to minus of gx for all x belonging to S2. But it is not possible because of the previous result. Hence, there exists some x in S2 such that fx is equal to f of minus x. So, we have proved BorsaCoulomb theorem and Brouwer's fixed point theorem for dimension n equal to 2. Before we conclude, we just point out that these theorems hold for any dimension n. But unfortunately, fundamental groups are inadequate to prove these for any dimension n greater than 2.